Hi everybody, these are notes for 4.2b. Last section was 4.2a where we talked about graphing in standard form, or in slope-intercept form, and now we're going to talk about a different method of solving systems of equations where there are two equations that work together. When we talk about substitution, most importantly we're talking about replacing one value with another. So one of the things that we'll talk about is how these two equations can work together depending on how they're set up and what form they sort of take originally. One of the things that we want to focus in on first is our vocab. So we have the word substitution. You do this a lot and don't really necessarily think about it. When we have two different values that are equal to one another, then we can substitute one for the other. So if we know the value of a variable, we can substitute that value for the variable, or we can talk about how we can represent different expressions that have the same value in the same way. One of the most common ways that we do this is in algebra. So let's say that you know the value of a variable. You might know, okay, x is equal to -1. So in a given expression, excuse me, for example, like 3x minus 5. If you're talking about how you know the value of x is -1, then in that expression you can substitute the value -1 for x, and that will allow you to find a simplified value of the expression. In this case, 3 times -1 is -3, and then when I subtract 5, I get the value of -8. So the practice of substitution is where we replace one value with another. Sometimes it might be another expression. It just sort of depends. We have these two different representations of a system of equations where we might use substitution. The first one is where y is equal to 4x plus 1. That's the first equation. And the second equation is y equals -3x minus 6. Things that you want to notice here, especially about this particular type of system of equations, is that it looks a lot like what we did in the last section, 4.2a. The key feature of this particular system is that both of the equations are already in slope-intercept form. So notice how we're already in the form y equals mx plus b. We've already got all of that happening. This means that both of these expressions are equal to the same thing. So both of these expressions are equal to y, which means that we can set these two expressions equal to one another. And when we have this, essentially what we're doing is we're substituting, and we're saying, I know that 4x plus 1 and -3x minus 6 are both equal to y, and that means that those two expressions must be equal to each other. And we've seen equations like this where we have a variable on both sides, so we'll solve that one in a second. However, it's not the only type of system of equations you'll see where we use substitution. The second type of system of equations is where not both of them are in slope-intercept form. Only one of them, especially if you're looking at the second system in our little box here, is in slope-intercept form. So the first equation is actually in standard form, which means that both of the variables are on one side and the constant is by itself on the other side. And then the second equation is in slope-intercept form, which means that the y is by itself, but the mx and the b are not by themselves. So one of the things that makes this a different type of system is the fact that one of the equations is in slope-intercept form and the other equation is in standard form. And the reason that this is worth mentioning is because it's not always going to work out that your system of equations is going to be nice and have both of your equations in slope-intercept form. It just doesn't happen very often, so we want to be prepared for all of the different things that could happen. Now, let's fill in our boxes, our blanks, excuse me. The first equation is the one in standard form. The second equation is the one that's in slope-intercept form, just in case we're remembering our vocabulary and we're paying attention to what we're doing here. Goodness, excuse me. Okay. What we're going to do now is actually go ahead and solve both of these systems of equations, and let's use our different techniques. So we have different ways that we will approach both of these systems because they are set up differently and they present differently. The first thing that you want to do when you notice that both of the equations are already in slope-intercept form is take each of the expressions that are on the right side of the equal sign and go ahead and set them equal to each other. And you're able to do this, remember, because it's a y equals in front of both of these. So imagine that instead of a y, maybe it was like a 6. Each of these is equal to 6. And then what we can do is get rid of that y because I only want one variable and I can set them equal to each other. So the first expression is 4x plus 1, and then the second expression is -3x minus 6. And if I put both of these on one side of the equal sign, Now I can solve an equation and I can find the value of x. Essentially what I've done here, if you're like, how was she able to do that? Essentially what I've done here is I've replaced each y with its actual expression that contains the variable x. And so now on each side of the equal sign, I only have one type of variable and I have constants only. This is where I get to follow our old time-tested acronym, don't call me after midnight. First I would distribute, but I don't have any sets of parentheses. Then I would combine like terms, but I don't have any of those either, which means my next step is to move the variables. This is something that I can do, so I have to decide where I want all of my x's to be. I personally don't like to have a negative coefficient, so I'm going to add 3x to both sides of the equation. You could also subtract 4x if you wanted to. It really doesn't matter. After you've moved the variables, what you have to do is you have to pay attention to where all of your moving parts are. So where are the variables and where are the constants? 4x plus 3x makes 7x's, and then the positive 1 just drops down. On the right-hand side, negative 3x plus 3x is 0, so the negative 6 is the only thing that's there, and this is a two-step equation. My next step is to either add or subtract. Since it's a positive 1, I need to undo the positive, and I need to subtract 1, and I'll have to do that from both sides of the equation, the left and the right-hand side. Now, if I subtract 1 from the left and the right, I'm looking at a one-step equation here, and I'm very, very close to the end. So let's see what happens here. 1 minus 1 is 0, so the only thing that's on the left-hand side is the 7x's. On the right-hand side, I have negative 6 minus 1, which is negative 7. I would like to get this x by itself, so my last step is to undo or to either multiply or divide. That's what the M stands for in Don't Call Me After Midnight. If it's 7 groups of x, that's great, but I don't want 7 groups of x. I want one group of x. So I have to undo the multiplication, or I have to divide by x on the left and the right. 7x divided by 7 is a positive 1x, and negative 7 divided by 7 is negative 1. So I end up finding out that the value of x is negative 1. And you might be thinking, okay, I'm done, it's over, that's great. Not quite. We're not there yet. We have to find out the solution to the system of equations. And a solution is always an ordered pair, which means I need an x and a y. However, since I have the x, I can use substitution again. This is why it's called substitution. Well, it's one of the many reasons it's called substitution. And I can say that what if I were to replace the x with a negative 1 in either one of these equations? Now, it doesn't matter which one you do, but I like positive numbers. So I choose to plug into y equals 4x plus 1. But it really doesn't matter. It's going to be a solution to both of these, so it doesn't matter which equation you pick. Both of them will give you the same number, and you can always try it if you'd like to. You can check your answer however you'd like. But me personally, I like a positive number, so I'm going to choose y equals 4x plus 1. That's going to be the equation that I'm going to plug my x into, and that's how I'm going to find the y to finish this particular problem, because I need an x and a y. I have to have an ordered pair. So if y is equal to 4x plus 1, the last step that I just did showed me that x is equal to negative 1. I can get rid of that second variable, and now I would only have y if I say that x is negative 1, and 4 times x is really 4 times negative 1. Then I still have to add the 1 in. 4 times negative 1 is negative 4, and negative 4 plus 1 is negative 3. So I just found out that x is equal to negative 1 and y is equal to negative 3, which means that as an ordered pair, I would have negative 3, comma, or negative 1, comma, negative 3. So I said that in the opposite order that I meant to. One of the nice things about this type of system of equations is that it's already in slope-intercept form, both of them. So if you wanted to graph and you wanted to say, I wonder if I did that math correctly, you definitely could. Desmos is also a nice option. But if you wanted to graph these, there is a coordinate plane attached. Just gives you the opportunity to kind of see, okay, did I do this right, and what might it look like visually? Your first line is y equals 4x plus 1. All of these are positive numbers, which is nice. The positive 1 tells you that from the origin you would go up 1, and that's your y-intercept. Then your slope tells you that you need to go up 4 and to the right 1. Or you can go down 4 and to the left 1. And I like to do 1 point in each direction, connect your line, make sure that there's arrows on both sides, and then this would be the line for the very first equation in the system. The second equation is y equals negative 3x minus 6, and I realized that I did opposite color coordinating here. Just pretend that didn't happen. The negative 6 tells me that from the origin I need to go down 6, which is the very last point that I have on this y-axis. And then the negative 3 tells me I should be going down 3 into the right 1, but I can't do that. Instead, I'm going to go up 3 into the left 1. And when that happens, oh, look at this point right here. I've got an intersection, but I'm going to do that one more time just so I have 3 points on my line. Connect. And then look at where that point of intersection is. Something that should happen is that this intersection point should be the exact same ordered pair that I just found as the solution to the system of equations. I went to the left 1 and then down 3. That gives me the ordered pair negative 1, negative 3, which does in fact match my system of equations solution that I just found with substitution. We've got another example. Okay, here's our next example. Excuse me. This time we have where y is equal to 3x plus 5 and 6x minus 3y is equal to 9. Our first step here is going to be to substitute. And look at that 3x plus 5. It's going to go in for y in our first equation. And what I mean by that, excuse me, is that if I know that y is equal to 5, or y is equal to 3x plus 5, what I can do in the first equation is I can replace the negative 3y with negative 3 times 3x plus 5. And then, after I've done this substitution, look at how the equation only has one variable. There are no more y's, it's just x's. And this is a good thing to happen because that's the goal of substitution. I have to continue, so the next steps are all going to come from don't call me after midnight. This time I do have a set of parentheses, so I have to do the distributive property. There's no way around that. What's being distributed is a negative 3. So the 6x gets to come down. I've got negative 3 times 3x, which is negative 9x. And then negative 3 times 5 is negative 15. So the negative equals to negative 9 just gets copied down on the right. And now I have to kind of look at what happened because there's no more y, there's only x's, and the next step is to combine like terms. I have a 6x and a negative 9x, and those are the only like terms that I have. So 6x minus 9x is negative 3x, and then the negative 15 and the negative 9 drop down, equal sign stays where it is. This is a two-step equation. I like these, I've done these before. My next step is to add or subtract. In this case, since it's a negative 15, I have to add 15 to both sides. So I've got negative 15 plus 15 and negative 9 plus 15. On the left-hand side, negative 15 and 15 make 0. So the negative 3x is going to drop down, and the negative 9 plus 15 is positive 6. So what I end up having is negative 3x is equal to positive 6, but I have to get the x by itself, so I divide by negative 3 on the left and the right. Negative 3x divided by negative 3 is 1x. 6 divided by negative 3 is negative 2. We're not done yet, though. We have to do some more substitution. I need an ordered pair, which means that if I have an x value, I need a y value. I'm going to do some more substitution. This time, I'm going to substitute the negative 2 in for x in either one of these equations, but the second equation is going to be a little bit easier. Since I'm solving for y, and the second equation already has that y is equal to 3x plus 5, I'm going to use that one. Because on the right-hand side, all I have to do is tell myself that wherever I see an x, I need to replace it with a negative 2. So 3 times x is now 3 times negative 2, and then the plus 5 just gets carried along. 3 times negative 2 is negative 6. Negative 6 plus 5 is negative 1. So that means that in this particular system of equations, x is equal to negative 2 and y is equal to negative 1, or as an ordered pair, negative 2, negative 1. As always, you can graph if you'd like to. This is going to be a little bit more work to graph as a system of equations, but it doesn't mean that you can't do it if you want to check and make sure that you did it correctly. The first equation is already, or the second equation is already in slope-intercept form, so that's the one that I chose to graph first. Y equals 3x plus 5 means that from the origin I need to go up 5, and then that's my y-intercept. The positive 3 over 1 as my slope tells me to go up 3 into the right 1, but I don't have room. Instead, I'm going to go down 3 into the left 1, and I'm going to do that one more time. And then there's my line. When I try to draw the straight line and connect the dots, it's just not really working for me all that well. I'm not sure what happened there. I tried. And then arrows on both sides. Excuse me. This first equation was not already in slope-intercept form, so I'm going to use the margin out here to the side, and I need to put the first equation in slope-intercept form because I can't graph this in standard form. 6x minus 3y is equal to negative 9. If I want this in slope-intercept form, I need to get the y by itself. So my first step is going to be to get rid of the x's. I subtract 6x from the left and the right. And then 6x minus 6x is 0. So I have negative 3y on the left, and that's equal to negative 6x minus 9 on the right. I went ahead and I switched the order of the terms because I like to already have it in a slope-intercept form. And then my last step is to divide out the coefficient of y, which is a negative 3. Negative 3y divided by negative 3 is positive 1y. Negative 6 divided by negative 3 is positive 2. And negative 9 divided by negative 3 is positive 3. So the positive 3 tells me to go up 3 from the origin. And then my slope is a positive 2 over 1. So I'm going either up 2 into the right 1 or down 2 into the left 1. It's actually the down 2 and the left 1 that's going to get me to the intersection point. This is such a weird looking set of lines. There is an intersection point, and there is only one. It really looks like there's more than that, but remember I did not do a good job drawing my green line. So when I look at this ordered pair, the point of intersection is still to the left, 2, and then down 1, which means that my solution of the systems of equations was done correctly with substitution.